Okay, so we continue our discussion on different properties of ideal fluids. So in this part, we discuss a very interesting theorem. It's called Kelvin's vorticity theorem. Okay. So from the previous discussions, we already saw that if we are taking an ideal but incompressible or barotropic fluid, okay, then the vorticity equation or the evolution of the vorticity vector, once again, just in case you forgot, the curl of the velocity is known as the vorticity vector. So the vorticity vector basically follows this type of relation. This del t of omega is equal to curl of v cross omega, where v is the bulk velocity. Okay. So if any vector q satisfies an evolution equation of this type, for example, del q del t is equal to curl of v cross q, where v is the velocity or bulk velocity of the fluid. So then basically this vector should follow a specific property, and that is, or should follow, so-called vorticity theorem. Okay, and what that is, that's exactly what we are trying to discuss now. So this theorem was for the first time discovered by Helmholtz in the year 1858, and then the current form of this was first worked out by Kelvin 11 years later. But somehow people call this now more popularly as Kelvin's vorticity theorem. Yeah, so in some places you can also hear the name Kelvin-Helmholtz vorticity theorem. Okay, so this proof of this theorem is not really very much essential for our course or for our purpose, but once again, if you are interested, so you can just check this any standard fluid mechanics book or over internet. Okay, there are so many literatures on that. So the statement is, let us assume the motion of an imaginary fluid surface. So in a flow field, you imagine or assume an imaginary fluid surface S. What is the meaning of fluid surface? That means a 2D surface, okay, a 2D plane type of thing, okay, which is made up of fluid particles. Okay, so this is not something where there is no fluid particle. That is not possible. So this is an imaginary 2D entity constituted by the fluid particles. If the vector q satisfies the above equation, this equation, then the total flux of q across this surface is, okay, which is given by integration, surface integration of q dot ds, will be a constant in time. That means, what is the meaning of that? That means that, let's say we are considering a flow field like this, okay, and inside this flow field we consider some arbitrary surface, okay, fluid surface S. Now as the fluid particles are moving, then basically this imaginary surface will also move. Let's say they are now moving to this part. Of course, in the course of the motion, the surface can change its area, but we are just tracing out all the particles which were primarily constituting this surface, and if we trace that in that collection of particles intact, then we will see that this area is now this area, okay. And now we calculate the omega at every point of that previous surface Okay, and we calculate not only omega, actually now we are talking about some arbitrary vector q. So for q we calculate q dot ds at every point and then we integrate over that surface. And if you calculate the value of this q vector at every point at this where the surface is now, and then we do a surface integral, then we see that in both cases the total surface integral has the has the same value. So in another way of writing, we can simply say that ddt of this integration of q dot ds is equal to 0. Now remember, this ddt means Lagrangian or material derivative. Okay. Now this simply says because we are now tracking the particles. Now not one single particle but one area or surface of particles. Okay. So that's why this is the Lagrangian time derivative of the whole flux, that is 0. That means this is a Lagrangian invariant. Okay. So or it is invariant over time along the flow. Okay. So for an incompressible or barotropic ideal fluid, of course, omega behaves like this q. And that's why the theorem simply says that for this type of incompressible or barotropic ideal fluids, ddt of integration surface integral omega dot ds is equal to 0. So that is the so-called Kelvin-Helmholtz vorticity theorem. Okay. Now I can do some mathematical reductions from this, which simply says omega is nothing but curl of v. So this is nothing but ddt of integration surface integral curl of v dot ds is equal to 0. So that is the statement of Kelvin's theorem. And by Stokes' law, this is equal to the closed line integral. Okay. So this closed line integral will be basically done on the contour of the surface S. Okay, the closed line integral of v dot dl. Okay, and so basically ddt of that closed line integral is 0. So these are two equivalent statements of Kelvin's vorticity theorem. Okay, this quantity, this line integral of v dot dl, is known as circulation vector. So another equivalent way of saying Kelvin-Helmholtz vorticity theorem is that in an incompressible or barotropic ideal fluid, the circulation, okay, the circulation across any surface, basically the circulation across any fluid surface, that is important, fluid surface, is a constant in time. Okay, so it is given that we are tracing the surface along the path of the flow. Okay, so basically this means that we are tracing the fluid particles along their real motion. Okay, and what is the physical meaning of that? That is something very important, and that actually will be used when we will even talk about like plasmas. Okay, because you will see that there will be something called magnetohydrodynamics when we talk about plasma fluids, and then B, or the magnetic field, will actually satisfy this type of equation, okay, and for ideal magnetohydrodynamics case. Okay, so what is the meaning of that? When some vector omega or q basically satisfies this vorticity theorem, the meaning is that the vortices, okay, so here simply for our case this means the vortices, okay, or the vortex, but it's not the vortices. I should write this properly, the vortex lines. Okay, the vortex lines, you can write also, yeah, okay. So the vortex lines, they are actually frozen along the fluid flow. Okay, what is the meaning of that? That means the total lines of vortex, okay, total lines of vortex, so vortex lines which were the total number of such vortex lines which were passing through this surface is actually not changing. So they are the same number of vortex lines are now passing through this surface. Okay, and that's why basically you can say that and this is the flux, this is the flux of vortex. Okay, and so if that does not change, they simply say that whenever the fluid is flowing, so along the fluid flow the vortex lines are moving so that they are stuck to the fluid flow or they are frozen in the fluid flow. So in a sense this is also called a frozen in theorem. Okay, so this thing has very importance, I mean very deep importance in various things in astrophysics. Okay, so maybe when we will discuss different type of instabilities or some other astrophysical examples, we will come into that. Okay, thank you.